The Fischer projection is used for compounds that have multiple chiral centers. And in that instance, Fischer projections really excel. When the compound only has one chiral center, it's not particularly useful. But Fischer projections have some fairly specific rules about how they are constructed, and it is important that we observe some of those. So in general, if we want to talk about a compound that has a Fischer projection or something really, really simple, we can just draw something that is CH2OH, and you've got something that comes down here, and then it's going to go over here to CH2, CH3. Then you've got chiral center that there's an H in the back, and then, why not a bromine? So that's not elegantly drawn, but there is a specific way in which a Fischer projection is drawn. A Fischer projection is ideally to make this whole chiral center look like a plus, okay? And in this instance, it becomes a bit easier to visualize, right? If I could just draw out my molecule just like that without any dashes or wedges, and we could ideally just come to an idea as to what the stereochemistry is, because now I have converted this, all right, I have converted this into this. And in principle, and I'll show you how, in principle this is a much easier problem to solve when you're talking about stereochemistry, because in this case, okay, in this case, you have to follow your rules where the hydrogen is in the back, and this time the hydrogen is in the back, so that makes everything quite simple. And we have to do the numbering, and we'll figure out the R and S of this one because it's fairly straightforward. Because bromine is the top group, and then we look at the next one. That's a carbon and that's a carbon, so that doesn't add up. So what's attached to the carbon? There's an oxygen, and then there's a carbon here. So this is the highest priority because it's a CO as opposed to a CC. So then that's going to be 2. That's going to be 3. And then the one in the back is 4. All right. And we just now draw our circly bits this way, this way, this way. And we know that that is a clockwise rotation. So that has to be an R configuration. All right. That is not hard when the thing is already arranged, when the lowest priority is already facing away from you. That's a really simple thing to do. When the lowest priority is not, it's not. But when you have multiple chiral centers, doing that for each one, oh my God, that is going to be a pain. So Fischer projections help solve that. Obviously, it's not going to necessarily make this any easier, but why not? To find the chiral center in a Fischer projection, you do the exact same thing, right? Except there's an important caveat what a Fischer projection is. A Fischer projection is essentially another way of drawing this, where your hydrogens or your substituents are pointing up towards you, and these little bits are actually curled away. And I'll do more examples on this if it's not. But this is essentially what a Fischer projection is, right? It is still a tetrahedral carbon that is just drawn in a different orientation. And when you do that, you still find the chiral center in the exact same way. Bromine is still top priority. That's 2 and that's 3. And then you draw your arrows. And you'll notice, oh my God, it's going in the opposite direction. So then that must be an S configuration. What? But the Fischer projection I have drawn has put your high priority group facing you. And just as we had discussed, I don't know, somewhere, maybe not in this one, but in a prior discussion, if your low priority group is facing you, just reverse that letter. So in a Fischer projection, you go like this, you just, instead of calling it the R, it's the reverse. So, or I'm sorry, instead of calling out the S, it's just a reverse. That must be the R. And so, in that way, the Fischer projection and the Kahn-Ingold-Prelog rules are the circling is reversed because the low substituent or this substituent is going to be facing you. Okay, it's going to be facing you. So in any case, that truly is not where I think Fischer projections shine. You know, if we want to do a real good Fischer projection example, we got to have more chiral centers associated with it. And so let's just do this one. Okay, so we're going to do, I know we got an OH here, and now we're going to do a bromine and a hydrogen. Okay, I got a bromine and hydrogen. Okay. Now, if we wanted to draw this compound into a Fischer projection, we always have to make sure, as I said, that the carbon chain is the central bit, right? So when you draw your little cross thingy, your cross thingy has to be the carbon chain. It's always going to be this part, all right? And so in that cross section, you can draw, you know, the stereocenters if you want, so that that's like a bow tie sticking up at you. Okay, you don't actually have to draw it as a bow tie, but you can if you know you're inclined. And they are always sticking up towards you. And you'll notice that somehow this is up towards you, then this is somehow down facing away from you. So in order for these to both be popping up at you, right, you're going to have to spin this molecule on this side here. This is going to have to be spun around, right? So really, I'm going to have to redraw this in order to make it more compatible with a Fischer projection so that it looks like this, right? And if I do that, then I still have an OH here, okay? Whoop. This is still an OH coming out here. And this is still a BR and an H here, except now I have rotated around here, which means this is flipped around. So that means that the bromine that is coming out towards you is now on the other side. All right, so that means that the bromine is now on that side, and on this side is the hydrogen. And then that is still a CH2CH, right? So now I can go over here, and I can draw this OH. There's no chirality at that point, so it doesn't really make any difference. By Jove, I need to slow down. That's CH2, CH2. That's that feller. And then we need to draw this one. Okay, there we go. Now, we are going to use the old eyeball of science to try to look down here. This is where we need to look. We're going to stare down there. That's going to be our Fischer projection. And so if we look down here where this is the top, okay, that's going to correspond to that. Then the bromine is going to go on this side, and the hydrogen here, and then the bromine is going to go on that side, and the hydrogen is going to go there. Okay, and we can check these are the appropriate Fischer projections pretty quickly by assigning R and S stereochemistry on this carbon. Okay, so if we look at the first substituent off of that carbon, we see bromine is going to be number 1, and then we look at the next substituent. See here, both of them are carbons, so that's unhelpful. So we go to the next one, and then the next one is an oxygen, so that's pretty good. But this one's a bromine. So bromine is heavier than oxygen, so that means that this direction is number 2, and this direction is number 3. And so we just draw our line connect 2, 2, 3, 2, 1. That goes in a clockwise, so that has to be R. So let's confirm that this over here is R. And that's easy enough. Bromine is going to be 1. This is going to be 2 because That carbon is connected to a bromine. That carbon is connected to an alcohol. And bromine wins again, and that carbon is going to be 3. So 1 is going to connect to 2, and oops, that is going to connect to 3. Go back to 1. And now on this side, my circle is an S. But remember, we reverse the Fischer projection because the low substituent is pointing out towards you when the rules say it should be pointing away from you. So you got to reverse it. So even though this is counterclockwise, we call it an R in the crazy Fischer projection world. Okay? So that makes sense. And then let's do this one down here really quickly, right? So bromine is going to be 1. So that's definitely 1. There's no ambiguity about that. In fact, let's make that a different color so we can keep track of our stuff. Bromine is 1, and then let's see here. These two, that's a carbon, so no win there. That carbon is attached to a CH3, and that carbon is attached to a bromine, so when one attached to the bromine is going to be the winner. That one's going to be a 2, and then that one gets to be a 3. So we go 1, 2, 3, 1. That is a counterclockwise motion, which means that's an S, and that means we actually go the opposite direction, so it must be an R, and so we get 2 R's. So it's a RR23-dibromopentanol, okay, is the actual configuration. And so in that way, Fischer projections are modestly helpful. But what makes Fischer projections particularly helpful is not only can we pretty easily assign R and S stereochemistry, just follow the rules and then just reverse the R and the S, but they also help you to see if the overall molecule is chiral, okay? So what I have drawn here is a molecule that very clearly has 2 assignable stereocenters, and this molecule is chiral. Because our definition of a chiral center and a chiral molecule is that they have no internal planes of symmetry. And this molecule, it clearly doesn't have an internal plane of symmetry. But this is just one of 4 stereoisomers that this molecule can have, right? So if we consider, and let me get rid of this here, if we consider the other stereo configurations that this molecule can have, you have 2 chiral centers, 1, 2, and each of those chiral centers can be either R or S. So it is always your equation for the number of chiral centers that you can have, or the number of molecules based on the number of chiral centers is always 2 to the n, right? So either R or S, so that's 2, and then this n corresponds to the number of chiral centers you have. So you will have, if this molecule, for instance, is 2 chiral centers, it's 2 to the 2, so there's a possible 4 different ways you can arrange the B and the H's. So you can have, in that particular case, you can have RR, as I have drawn here. You can also have an RS, or you can have an S and you can have an R. That's 3. And then you can have an SS, and that's 4. So that just grows exponentially as you add more chiral centers. So let's draw out what those 4 chiral centers are, because this is kind of helpful. And let's use the Fischer projection, because the Fischer projection is truly helpful in this particular case, where we will now, I'll just write CH2OH, and then I'll write CH2CH3. And the molecule, the RR configuration that I just drew, is BRH and HBr. And we know that that is 1, okay? And then that molecule has an enantiomer, so it has a mirror image of itself, CH2OH, CH2CH3, and that mirror image is going to have a Br there and a BRH. So in this case, this is our RR, and then our mirror image, SS. Okay, so just scoot this little thing over. Now, what are the other 2, right? So we've drawn those 2, and then I told you the other 2 are where they're mixed, where one is an S and the other is an R, and then vice versa. So we've already drawn RR up here, so we can just draw the RS conformation, and that's pretty simple. So we'll just draw the R configuration on the top. That's an ugly Fischer projection. let's draw the pretty picture. Let's draw that a little bit neater. CH2CH3. All right, so we'll draw the R. Whoop. We're going to make sure that's a bromine. And then we're going to draw the S down here. So, no reason to be sloppy right now. All right, so I know that this one is R, and because I've solved it already over here. And I know this one is S, because I just drew the opposite of that. So that's the R and the S configuration. So this is actually, you can look, I mean, that's the S, that's the R, and that's the S. One thing you'll notice, though, is the relationship between this R and this S has no symmetry. There's no symmetry operations you can actually do to convert this one to this one, whereas this feller and this feller, these two are mirror images of each other. So these are truly enantiomers. Okay, so these two are truly enantiomers. I mean, the whole molecule are enantiomers of each other, not just the chiral centers. They're actually molecular enantiomers. And then these two, they do have a relationship. You don't see any symmetry. They are effectively different compounds because there's no symmetry elements to them. But their relationship is what are called diastereomers. So these two are diastereomers here. And that relationship is essentially they're the same molecular structure. There's the same constitutional isomers. They are not related by a mirror image, but they have the same connectivity and different stereo configurations, okay? And now, as I said, this was 4 of them. So this one does have a mirror image, okay? And that mirror image is we'll draw that one. And in this case, that's the H on that side, that's the H on that side, that's Br, that's Br. And you can, again, convince yourself that this is going to be the S configuration here. And we can say that's going to be the S configuration because we know that's still 1, that's still 2, and that's still 3. And we can go 1, 2, 3. And I'm rotating it in a clockwise direction, which is per the traditional rules R. But by the Fischer rules, we reverse that. So that's the S. So that's S. So I have truly drawn the opposite configuration. And then that's going to be the R. And you can do that if you want, but we can show that's 1, 2, 3. Connect 1 to 2 to 3. I am rotating that in the S direction by our typical rules, but Fischer rules reverses that, which makes that an R. All right. So these two on this side, these are enantiomers of each other. These two are enantiomers of each other. And these two are enantiomers of each other. But these two are diastereomers. And you can say the same thing all the way out here. These two pairs are also diastereomers. Basically, anything that is not a mirror image and has the same sort of configuration, these are all diastereomers. So the relationship between these two pair of systems are diastereomeric. All right, and diastereomeric pairs are important because enantiomers have identical physical properties. So you would expect that an enantiomer is going to have identical boiling and melting points. Diastereomers will have different physical properties. And that comes down to partly because they are allowed to adopt different conformational isomers at different times, right? So in the case of these pair, this pair of diastereomers, if you look, what you'll notice is that in both of these cases, I can actually draw on this side a dipole where these electronegative bromines are pulling electron density in one direction. Now you'll notice, relative to each other, they're in opposite directions. So comparatively, while these both have a dipole moment, they cancel each other out. Hence, the enantiomers, they have identical physical properties because they always cancel each other out physically. Just like in this one, these have no net dipole, right? They kind of have dipoles that do point in the right direction. They go that way and that way, right? So, and these have dipoles that are sort of pointing in the opposite direction. So they cancel each other out for each other. But overall, what you'll notice is that these systems have strong dipoles in some direction. These systems have dipoles that cancel each other out completely, which means that because these have dipoles, the boiling point of this compound is higher than the boiling point of that compound. That is a factor in enantiomers that makes them pretty, in diastereomers that makes them pretty cool. If you can, in fact, make a diastereomeric pair, if you can make a diastereomer, you can actually start separating things out with boiling points and physical differences like that, okay? But there's also something else about this that I think is very interesting. This is that while these systems are totally chiral molecules, they're an enantiomeric pair. I've called these enantiomers, right? Just to be consistent and say, you know, they're mirror images of each other and they're enantiomers. But they're actually not even chiral, right? Because they fail our first rule of chirality. And our first rule of chirality is that you can't have a mirror plane. And these have a mirror plane in them. And you can even see that mirror plane. Let me get rid of this arrow here. I get rid of everything, I suppose. Get rid of that. And you can see that there's a mirror plane here. Okay, now there is something that we should be aware of. Now that we've learned diastereomers and enantiomers, there's actually a trick that Fischer projections are pretty good at catching or helping you catch. What happens if with this molecule, let's say, so here in this particular case, I have made the top and different from the bottom, but you can easily have a compound that, can I go up here? Well, that's awfully coded in letters, but let's just steal this one again. I can copy, and let's just go back down here and paste. Okay, and let's see if I can surgically remove some of the well, that's good enough for me. Let's say you didn't have the alcohol on there, okay? Now this is an interesting example purely from the perspective of this being not a chiral compound at all. And what's crazy is you just saw me delete the OH, right? And I know it's not a chiral compound at all because I can draw a mirror plane through here, okay? And everything on this side of the mirror is going to be, well, doo-doo. Not the same, because that's not a mirror plane. Lol. That's why Fischer projections are so cool. Actually, the mirror plane is the opposite of that. It is the one where the BR is in the back. This is their mirror plane, right? And you don't notice it's a mirror plane, I guess, because it's the way it's drawn. That's not really looking like a mirror. But it will look like a mirror much more when I draw the Fischer projection, okay? And that's how we know, and that's why Fischer projections are so useful. Because if it's got a mirror plane through it, it's not chiral. That's them's the rules. And so let's draw little bow ties here. And remember we got to rotate about here. Let's get rid of that stupid because that's not intuitively helpful, but if we rotate around this, and our actual compound now, which would make sense, is going to be full on that. And that BR doesn't really change. And you will actually be able to see now the mirror when we bring it forward, because now that, which is supposed to be a BR now, whatever that is, and obviously it's a B lowercase r because we're using the periodic table last I checked. As we rotate that around, so now the bromine is actually going from behind to the front, and that's an H. Now you probably can very clearly see that there is a mirror plane once I've rotated this around. And in this particular case, now that I've rotated it around, what you end up with is it doesn't actually make any difference, right? That's what's so intriguing about these types of compounds is, you know, which side do I draw the bromines on? Because if I put my little eyeball of science on that side, or this side, you're supposed to look at it from this side, right? So you look down, and you don't really have like a good idea which one's the top. I mean, arbitrarily, I guess I could say if that's the top, then the BRs are on that side and that side. But there's no real reference here. There's no real reference for me to actually assure you that I am saying that this corresponds to this, because this it could also correspond. There's just no way for you to verify. Like, I cannot assure you with 100% assuredness that this corresponds to this, because they're symmetrical, right? So this whole getup, right, unfortunately can refer to both the R and the S configuration as well as the S and the R configuration, all right? Because there's just really no good way. I mean, we can assign R and S individually, all right, CH2, CH3. We can still draw an enantiomer here. All right, we can still do that. We can still number them and say, you know, that's 1, 2, 3, circling around. So that is then going in a clockwise direction. So that must be the S configuration. And number them over here. So that's 1, 2, 3, right? Because this carbon is attached to a carbon. That carbon's attached to a bromine. So that has to be 1, 1, 2, 3, circly. And that's the opposite direction. And so we flip that around. That's the S and the R configuration. And we can confirm it up here because I have essentially just taken the S and the R configuration of these two. So S and R where the bromines are pointing that way, S and R the bromines are pointing that way. But again, all I have to do in order to make these two compounds identical is go doop, 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 and then flippity, 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 flip. And yeah, now they're the same compound, although one is upside down and the other's not. But they are the same compound. Imagine all the letters flipped around at the same time. And if those two are the same compounds, then they are not actually mirror images. They're just the same thing. And that gives rise to a new term where you have what appear to be enantiomers, but they're nothing but enantiomers of lies. And they're called mesocompounds. Mesocompounds, also enantiomers of lies. Whatever makes you feel happy. But mesocompounds aren't chiral, because I totally just showed you why, hopefully.